This is the agenda for today. We will discuss about what is unsupervised learning, how can we use it. Then we'll go to discuss the unsupervised learning algorithms, k-means clustering, hierarchical clustering, and the Python codes for that. And like always, we would have the real world case study also to complement the knowledge, what exactly and where exactly you can use unsupervised learning in your day-to-day business problems or in your for your interviews, for your research purposes. Okay, so we know about supervised learning problems. In supervised learning problems, we have a target variable, a fixed target variable. In unsupervised learning algorithms, we do not have any target variable. Rather, we have only dataset, and we ask the algorithm to find the pattern in that dataset for us. Now that pattern can be anything. But we do not have any preconceived notions from our side, from human being side, that this is the target variable we want to optimize, we want to predict. No, we have the algorithm. Like on the figure, you can see that if you can classify it by colors. If you segment them by colors, it will be a different cluster. If you club them, if you aggregate them, you combine them by shapes, it will be a different cluster, right? So based on the type, or if you classify them by the size, it will be the third dimension, right? So based on the attribute you choose, shape or color or size, you are getting different results. That means what is important, what the important piece is that what attribute are you choosing to make the clusters or to perform this clubbing, this segregation of data points. So essentially what we want to do is we want to achieve something like this, that is there any pattern in the dataset which we can find, which the algorithm can find and use it for future analysis purposes. Yeah? That is the meaning of unsupervised learning. Unsupervised, we do not have any target variable to optimize, any target variable to achieve, right? So for example, if I go to the use cases of unsupervised learning, for example, let's say you have retail industry, you have an apparel selling, apparel selling business. Let me go over here to the Excel sheet and give you let's say a case study on that. Let's say you have a customer ID. You have customer ID, you have the revenue from the customer, you have all the invoices generated from the customer, you have the number of items bought, you have the frequency of purchase, you have the date of joining. You have multiple attributes. So customer ID 1, 2, 3, 4, 5, and you have whatever revenue you have, whatever number of invoices you have, number of items bought, so on and so forth, right? Now, in the case of supervised learning algorithms, we could have a target variable which could be like whether the customer will shop or not. In the case of supervised learnings, we do not have this variable. Rather, we will have this data set and in fact 20-30 other variables, and we would ask the algorithm to find patterns in that without us feeding it any knowledge. The knowledge which we will be feeding is that which attributes, which variables should be considered while doing the analysis. That's it. Yeah. So, like for example, in a retail industry, you would want to create segmentation of your customers like this, and so that you can increase the transaction value, you could increase their basket size, you would want your customers to buy more and buy more often with you. If you compare, let's say, with telecom industry, in telecom industry, you can again find the customers, and you would want the customers to recharge more with you, to use your services more often, right? Same can be applicable for BFSI industry. Same can be done for healthcare, right? Where you would want to understand the genomics of the cells, of the protein cells, right? Now extend that to text data. So over there in the text data, let's say if you have 1,000 articles or 10,000 articles, and you would want to understand that, let me get the articles which belong to the same category. You can do that, or extend that to images, right? So, but that being said, clustering is not the only application of unsupervised learning algorithm. It is one of the most famous and widely used, but it is surely not the only one. So you have plethora of clustering algorithms. I have listed only the major ones over here: k-means clustering, hierarchy clustering, DB-scan, spectral clustering. There are other other clustering algorithms too. But apart from the clustering, we have principal component analysis, or PCA, singular value decomposition, right? Both of them, they can be used for your dimensionality reduction. What is meant by that? Typically in the real world datasets, you can get maybe 100, 200, 500 attributes, 500 or 200 variables, right? Now, analyzing all of those variables at the same time in the same analysis, it is quite complex. It raises to a phenomena called curse of dimensionality. Curse of dimensionality. Yeah. Curse of dimensionality. What it means is that you have so many variables and attributes to analyze, you can no longer analyze all of them simultaneously and effectively. And if you have, let's say you have 200 variables and you have only 1,000 or 100 data points, this further makes it much more complex. So PCA and SVD, they allow you to filter out, to get the most significant variables out of the entire data set. That is the application of PCA and SVD, and that is a very powerful application because the fundamental behind that is that if I have, let's say, 200 variables, not all the variables will be significant, not all of the variables will be important. There will be a set of variables which will be contributing the maximum. That means out of 200, it is a possibility that I have only 60 variables using which I can explain, let's say, 95% of the data or 95% of the variance in data. Okay. Now, for example, if I go back to the example of retail over here, and let's say this is the example of a grocery retail. So in that case, let's say if there's a variable of customers hair color, right? So in such a scenario, if this is grocery retail, or let's say apparel retail, the customer blood group, right? These variables, they will not be of much significance in making a prediction. So such variables have to be ignored, right? I just took an example, but in the real world scenario, there can be and there are variables which are of not much importance, and the objective of PCA and SVD and many other variables like that, they allow us to choose those significant variables from there. Association rules. Association rules are, again, like market basket analysis. They are the unsupervised. They can be called as unsupervised learning algorithms. Then you have neural network based algorithms, TSNE and autoencoders. They are, again, unsupervised learning algorithms which can be used for your images, which can be used for your text data. Okay. Today we are going to focus upon clustering techniques. In the next sessions, we will be talking about other unsupervised learning algorithms, but today we are talking about clustering techniques. So clustering techniques you can classify further as centroid-based clustering, density-based models, connectivity-based models, distribution models, and deep learning models. So centroid-based are The most famous one is k-means. K-means can have other versions like k-medoids, k-medians. Density-based model are dbScan optics. They are the most famous ones. Density-based means, so centroid-based means if you have a fixed centroid of the data set, then you can define your clusters. Density-based models are where the data points are connected in dense regions. Connectivity, that means what is the connectivity between various data points, that is hierarchical clustering. Then you have distribution models where you talk about what is the distribution of my data set, of all the variables in the data set, and then can I find patterns from there. And then you have deep learning models. So let's start with k-means clustering. Now before that, what do I mean by clustering? Now clustering as a technique, what is the objective over there? The objective is that can I club, can I cluster, can I segment the observations which are similar. Like for example, they might be similar observations, right? This is frequency, let's say 4 and 3, right? We remove this variable, and let's say 1001 invoices 5, items 500, frequency 10, right? And 1002 invoices 6, items 499, frequency 9, let's say. So in this case, in this very simple example, we can say that yes, these two customers, they belong to the same group. These two customers, they belong to the same group. So in a very simplistic format, this is the meaning of clustering. And wherein you want to segment, you want to create groups of observations which are of similar type, which have similar attributes, which have similar properties, right? The objective of the algorithm will be to find those groups based on the properties which we tell the algorithm to use. So then you have, the most famous one is k-means clustering. So what happens in k-means clustering is, now you have to pay attention over here, please. How it works, the k-means algorithm, how it works. So you have your data points at the start. Let's say your data points are like this, right? These are the data points. And your data points are like, I'm representing them, let's say on a XY axis. Simple. Okay. These are data points. So what happens in k-means clustering is, the process is that it initiates the clusters. That means, so you'll tell the algorithm that I want to have, let's say, 5 clusters or 3 clusters. Let's go with 3 clusters. So it will initialize centroids for those clusters randomly, completely random. Let's say this is the first centroid, this is the second centroid, this is the third centroid, which the algorithm initiated. Fair enough. Then you would choose the points nearest to that cluster. Okay, and let me put more points. Okay, so what would happen is, you would choose your points which are nearest to this cluster. So let's say we talk about this point. It will belong to cluster 1, right? This point, it will belong to cluster 2. So you keep on you assign all these points to a cluster, right? And based on that, let's say all these points, they belong to this cluster, and all these points belong to this cluster. Then based on that, you would recalculate your centroid, and again you would group the points which are closest to this cluster. Now what can happen is that, let's say this centroid, it becomes here. So earlier, this point, the point which I'm highlighting right now, it was belonging to cluster 1. Now it might belong to cluster 2. Similarly, this point, earlier this point was belonging to this particular cluster, it might start to belong to this cluster in the second iteration. and this process will continue. So again, I'll repeat, you will initialize your clusters randomly, the centroids of the cluster randomly, and and you will assign the points close to them, to that cluster. You would recalculate your centroids, and that assignment of the clusters will happen again. Then you would again recalculate your centroids, and the reassignment will happen again. This process will continue till the reassignment of the points does not give different results. Till that point, the process will continue. And once that end state is reached, once you cannot change your clusters anymore, we would say that yes, my clustering is complete. Now over here, I said we would assign to the same clusters based on what? There should be a parameter for that, right? The parameter is the distance, There can be multiple ways to measure that distance. The most famous way is Euclidean distance, which is like if you have 2 points, the way you can measure the distance between the two is the mathematical equation which we have studied in our lower standards, which is y2 square minus y1 square, right, plus x2 square minus x1 square whole root. I'm referring to this. Let me see. Yeah, let me check one thing here. So it is y2 square minus y1 square plus x2 square minus x1 square, right? So, and then you take a whole root of that. That is the Euclidean distance. There can be a Manhattan distance. Manhattan distance is like this. If this is the if they are the points, let's say, if they are the points, this is point 1, this is point 2. So Euclidean distance will be like this, straight. Your Manhattan distance will be like this along the straight lines, right? Or it will be same distance, I'm sure, but this is the meaning of Manhattan distance. Then there are other distances like Chebyshev distances is also there, but I won't discuss that. Yeah. Then comes your, so you have your k-means clustering like this. So the output will be, distance different clusters. I told you at the start that we have to tell the algorithm how many clusters we want. Do we want 3 clusters? Do we want 4 clusters? How to determine that? How many clusters you want? So for that, in k-means algorithm, we have a method called the elbow method. Okay. What it tells us is, like on the screen, you can see on the right side that over here, you would iterate with different values of k, with different values of clusters. So if I have 1 cluster, if I have 2 clusters, if I have 3 clusters, if I have 4 clusters, 5 clusters, and so on. On the y-axis, I can have distortion. That means what is the variance, or you can say distortion, in my dataset. And if I plot that, wherever I get the kink, I get a sharp edge like an elbow, that is my most optimal number of clusters. Okay, we will do that in the code, but just to let you know that this is the method you can use for finding the most optimal number of clusters. Okay. Then comes hierarchical clustering. Hierarchical clustering is again one of the very popular methods for clustering. It looks like a decision tree where you have a root node, then you split, right? Again, you would be defining the attributes. The data set will be given by the user, by you. And the algorithm will be using those attributes to split further. And what we will receive at the end is like a dendrogram that you can see on the right hand side. It's called a dendrogram. So these are the observations 1, 2, 3, 4, 5, 6 till 10. They are different observations, and what it tells is that this is the first observation. Yeah, this is the, let me see. Yeah, 1 second. Yeah, so what it means is that this is my cluster at the top level. This is my first cluster. At the bottom, they are my, if I keep all the observations individually, they are my cluster. So what it means is that each observation is one cluster in itself, right? So this is the top, this is the bottom. In between, you can see that if I cut my dendrogram like this, if I cut my dendrogram from here, I'll get 1, 2, 3, 4, 5 clusters. Okay. If I cut my dendrogram from here, I'll get 1, 2, 3, 4, 4 clusters in such scenario. If I cut it from here, I'll get only 2 clusters. Okay. So using the dendrogram representation is for how I can club all of my observations based on some of the attributes. Okay. This is the hierarchical clustering. We will again see that in the code. Okay. Now hierarchical clustering is again a very famous clustering methodology. Along with k-means clustering, hierarchical clustering is again very heavily used. Okay, both of them are very very popular clustering methods, and we use both of them to make make any clustering or segmentation decision in our day-to-day problems. Like you would not test your algorithm with only one. You would not test your solution with only one algorithm. You would test with more than 2 or 3 algorithms. And generally, k-means clustering and hierarchical clustering, both of them, they are a contender for that, right? So let's go to the code now. In the code, we will go through the concept of both k-means and hierarchical clustering again. We will show that we will analyze that how can we use the scikit-learn libraries, how can we visualize the clusters both for k-means and hierarchical clustering. Okay, again these codes, these slides, they are checked in at GitHub, right? Okay, so first is the k-means algorithm. So we have the data sets over here. I'll go to that. First of all the regular libraries we are importing: matplotlib, scikit-learn, pandas, seaborn, right? Seaborn is for visualization, matplotlib is for visualization, pandas, numpy are most famous libraries for Python, and scikit-learn is for my machine learning library or my data science library that I can use for. Okay, so data set is dead. It is a depression data set, and in that data set we have these 6 variables. 7th variable is ID. So simplicity, fertilism, depression, adjusted variables, adjusted values of them. Okay, now we are removing ID as a very first step. It is not required, so the ID is removed, and now this is the info of my data set. So I have these 6 variables, and this is my data set. That's it. Now I want to use k-means algorithm to find the patterns in this data set. Okay, so this is my data set. I did a describe. That means I want to see the range, the min max values, different percentile distribution, right? Okay, now over here using Seaborn, I can generate the plots for each of my variables, right? So the one over here, you can see that. Let me take the drawing tool. Yeah, so this one over here, this is the variables representation with itself. Okay, over here they are the respective scatter plots. So each of the variables a relationship with other variable. Like over here you can see that there seems to be a linear relationship. There seems to be some relationship over here, but not that strong. Like this relationship is quite strong. This relationship is not that strong. Okay, So what this plot will tell you is how are the variables working with each other? Is there any kind of correlation with each other with the variables, right? And this will allow you to choose the most significant variables. Okay. So just to add over here, it is not necessary for us to take all the variables, right? Let's say if we have 20, 30, 50 variables, it is not required for me to consider all the 50 variables. I can choose, let's say, 25 of those variables, and over there, PCA can help in making that choice. We will be exploring PCA in the next session, but just for today, PCA can help me in making that choice of those variables. Fair enough. Now, what to do? Now, first of all, we are scaling the dataset. What is the meaning of scaling? I am normalizing that. That means I am putting the mean as 0 and the standard deviation as 1. Okay, so using the z-score, I can do that. And now comes my clustering. This is the elbow method, which will tell me that what is the optimal number of clusters. So how do I do that? So from the SciPy library, I'm importing my distance matrix, and I am iterating from 1 to 10 clusters. That if I have only one cluster, what is my output going to be? If I have 10 clusters, what is my output going to be? Okay. Then we are iterating for all the values of k from 1 to 10. So k means cluster is the model which we have invoked. Fit the dataset which we have used earlier, which we have created earlier, and then after fitting, simply predict for each observation the cluster it has. Okay, and then we are talking about the distortion in the dataset. Okay, so what is a distortion in my dataset based on my centroids, and I want to use Euclidean distance as my distance measurement metric. Okay, so till this step over here, one second, till this step over here, my clustering is done. Exact clustering is over here. So k means this is this method, right? This method is performing that clustering for me. Okay. So again, a thought over here that you can see that creation of a machine learning model that we have seen in supervised learning too, creation of the model is not that difficult. Getting the data set in the correct form, that means the data preparation, and understanding the results of that algorithm, they are difficult, or they are time consuming process. In fact, getting the data is the most time consuming process. Okay, so you created your algorithms, right? And after that, we are simply plotting them. We're simply plotting them over here. We are simply plotting the number of clusters, and with that, what is the distortions I have. Based on that, we can take a decision that what is the optimal number of clusters we should have over here. So you can see over here that I have my distortions and I have my values of k. Now there does not seem to be a very visible kink. This also is good. This is also good. This is also good. This is also good, right? What should I do? So there are some practical applications you can do over there. First of all is that you test with different values, which we will do. You will also look at the ease of maintaining the clusters. What do I mean by that? If I take 5 clusters, right, and the values of clusters are like this. Let's say if I take, let me take 3 clusters, 1, 2, 3, and one cluster has 500,000 values. The second cluster has 5,000. Second has 50,000. Or let me make it 1,000. Now you can see that to maintain the 500,000 cluster, it will be quite a pain for me. Yeah. Instead, I would prefer if I can have, let's say, 5 clusters, 1, 2, 3, 4, 5, and each having roughly, let's say 40K to let's say 80K or let's say 60K, right? That will be much more better for me. That will be much more manageable for me. Let's say 80K, right? So because I want to have manageable clusters which can be used. Similarly, if I have, this cluster number 2, I won't want to keep it as a completely separate cluster. Or let's say, you would want this cluster to be combined with someone else, with a different cluster, right? So what happens is, practically, you break your clusters, your bigger clusters, into subclusters. Like for example, this 500,000, you might break into a 200K and a 300K, something like that. Or you might break that into 100K, 200K, 200K, right? Which are much more manageable than 500K. Similarly, this very small cluster, you might club this with this one, right? With this one, you would club it, that okay, now instead of 50,000, make it 51,000. And obviously there should be some similarity, then only you would merge it. If there's no similarity, you will not merge it. You will keep it completely separate. But in the real world datasets, you would find some patterns which would allow you to merge them. Okay. So coming back to the code, yeah. So I'm testing with different values of K, and based on that, I'm getting different values of centroids. Okay. So I'm for different values of 1 and 2 and 3 and 4, I'm getting my different values of centroids. And then I would want to, like, over here, for each of the observation, we have assigned a label. We have assigned a cluster label to that. Okay. And then I would measure the accuracy of my method. Now, for measurement of accuracy, there's a parameter called Silhouette score. So simply put, it measures the purity of your data set. Okay. So what it does is, you would, one second. Yeah. Silhouette score, what it does is that it measures the purity of your clusters. That means the idea is that your cluster observations, right? Observations in one cluster, they should be closest to each other, right? And they should be farthest to the other cluster. So Silhouette score, it measures that for you. Okay. I do not have implementation of Silhouette scores in this notebook, but I will complete that Silhouette score implementation too and upload that to GitHub again. But that being said, I have completed the entire K-means clustering over here, so you can use that. Then how can you visualize your cluster? So this is the 3D plot of K-means clustering, of you to visualize your clustering output. Okay. If I try with 2 clusters, these are the respective groups which I get. Okay. Now over here, we have shown the box plot also. Like if I have different clusters, what is the box plot of them? So if I have 2 clusters for adjusted depression, you can see that the box plots are quite different, and that is the objective. We should have different values of distributions for my different clusters. Okay. And finally, on a line chart, we have shown the relationship between different attributes, which is not very important for unsupervised learning, but we have at least shown that. You can use this code from GitHub. You can take the data from GitHub and replicate the results. For hierarchical clustering, again, we have done the similar stuff. We imported the libraries, my Seaborn library, Matplotlib, Pandas, NumPy, etc. We took the dataset. We have the dataset as name, average monthly spend, number of visits, apparels, all of that. And then I looked at the top 5 rows, scaled them, like we did earlier. Okay, and this is the seaborn for them, the pair plot. Now for hierarchical clustering, we have something called a agglomerative clustering. Agglomerative clustering, it is similar to your hierarchical clustering only, and we gave it the input parameters which you want to have. Number of clusters is 3, affinity is equal to Euclidean. Linkage is average linkage. So there are different types of linkages you can use in your hierarchical clustering methods. Like based on the relationship you want to have in your data set. I'll come to that at a later point, but for the time being, let's move ahead with the clustering. So we created the clustering and we grouped by labels, and all of that, and I created the dendrogram. This is the dendrogram which I can have in my hierarchical clustering algorithm. Okay, you can see that over here, different clusters, different observations we have, right? And we have different representations over here. Okay, now what it means is, if I change my clusters, if I change my matrices over here, instead of linkage, instead of word linkage, instead of over here, first we took which linkage? Average linkage, right? Instead of average linkage, if I take a complete linkage, my clusters, they change. Instead of complete, if I take a word linkage, my clusters change, right? So what is the meaning of linkage in my clustering algorithms, right? What it means is, you have different types of linkages. You have something called a single link, right? Then you have a word, you have a complete, right? What it means is that if you want to simply, measure the distance between your observations, like in the case of single linkage, you would measure the smallest distance between the observations, right? In the case of single linkage. Okay, what it means is that if this is your data set, 2 clusters, right, and this is one variable, this is one observation, you would measure the smallest distance between them. Okay, complete distance, or complete, it means the largest distance. That means if you have, let's say, in this cluster you have this observation, in this cluster you have this observation, complete will be this distance. Okay, and average will be the average of the distances between the 2 observations. Okay, apart from that, you have one more linkage method which is called the word linkage. Word linkage, it is based on variance. Okay, so the criteria is that we would be choosing the clusters based on the variance. Like the function is that I want to minimize the variance over here. Okay, and that is why it is called, this method was given by Wards, and that's why it's called Wards method. Yeah, right. So this is the Wards minimum method. Okay, now what it means is that I have different methods to measure the similarity, and based on that you can see that my values of hierarchical clustering are giving me different dendrograms. Now over here it is up to me which clusters, or what is the most optimal number of clusters I would want to choose. Now that is also an art. You cannot choose the number of clusters randomly. you would choose them by using a particular logic. Like over here, if I choose only two clusters, you could see that that might not be the most optimal solution. So the method for that is that we take a cut over here. I'll make a cut over here, right? And if I move this line up, what is the maximum distance I can take it through without having a different number of clusters? So over here I have 1, 2, 3, 4, 5, 6 clusters. If I move it up over till this point, it is giving me 6 clusters. Okay. If you take this one, the second one, which I'll take a different color, let's say green. If I make this cut, right, it is giving me 1, 2, 3, 4, 5 clusters. If I move it up, right, this is the number of clusters I can get. So you can see over here, between, if I move 6 to 6 and 5 to 5, the distance is higher. Whichever cut gives me the maximum distance, that is my most optimal number of clusters. So over here, I would try to make more cuts, and wherever I get the best number of, or the maximum distance, that is my most optimal number of clusters in the hierarchical clustering algorithm. That's it. Yeah. Now, you would, in practical real life scenario, again, by getting the number of clusters, that the next step is that how do I implement that clustering algorithm in real time, right? So you would create your clusters, you would, let's say using k-means or using hierarchical clustering, you will get the most optimal number of clusters, and then you would assign to each and every observation a cluster value, and then you would do the EDA, exploratory analysis of your dataset based on the clusters, right? Based on the clusters, you would do the exploratory analysis of dataset. That means if I have, let's say, 1, 2, 3, 4 clusters, what is the number of observations in each and every cluster, right? What is the, let's say average revenue, average number of visits, right, in each and every cluster. And what we would want is, we would want those numbers to be different. Like over here, the average revenue should be 100. It can be, let's say, 500 over here. It can be 10 over here. It can be 1000 over here. Okay. Number of visits can be, let's say, 2, can be, let's say, 5, 1, and or let's say 10 over here, right? So we can see that these 4 clusters, they are quite different from each other, and that is the objective of my clustering. I want to create the clusters which are very different from each other. Okay. If I observe something like this, 101 and 2, in that case, something wrong has happened, because these two clusters, cluster 1 and 2, they look the same. Okay. So if that happens, there can be other variables which are creating that differentiating pattern. But let's say in this case, if I have only these observations or these variables, then something is wrong for sure in this clustering algorithm, or in this clustering method, wherein I have got 2 clusters which are similar. In that case, you should have a relook at your clustering. Okay.